Hello, and welcome to today's lesson on the emission of infrared radiation by objects. In today's lesson, we'll begin by exploring the emission of radiation by objects. We'll then learn about the relationship between intensity, wavelength distribution, and temperature. So far, you have explored the basic properties of waves, including their nature, types, and behavior. You have learned about reflection, refraction, and diffraction, which are all foundational concepts in wave physics. Building on this foundation, we can now examine how infrared radiation is emitted by objects in more depth. Understanding how objects emit and absorb infrared radiation will enhance our overall comprehension of thermal physics and energy transfer processes. All objects emit radiation due to their temperature. This emission is primarily in the form of infrared radiation. As you now know, infrared radiation, also known as thermal radiation, is a type of electromagnetic wave, just like visible light and radio waves. An important point to note is that good absorbers are also good emitters. This is governed by the principle that an object that absorbs radiation well at a particular wavelength will also emit radiation efficiently at that wavelength. For instance, a black, dull object absorbs almost all the incident radiation and is also a good emitter of radiation. On the other hand, a white or shiny object reflects most of the incident radiation and is a poor emitter. The intensity and wavelength distribution of the emitted radiation depends on the object's temperature. The intensity of radiation increases with an increase in temperature. This means that hotter objects emit more energy per unit area per unit time compared to cooler objects. To visualize this concept, we use a blackbody radiation curve. A blackbody is an idealized object that absorbs all incident radiation and emits radiation purely as a function of its temperature. The blackbody radiation curve plots the intensity of emitted radiation versus wavelength for different temperatures. As the temperature of the blackbody increases, the curve's peak shifts to higher intensities, indicating that hotter objects emit more radiation. We will expand on these ideas in subsequent lessons, so don't worry if they feel a little complicated for now. Another crucial aspect of radiation is the relationship between wavelength and temperature. The wavelength at which the peak of the radiation occurs depends on the temperature of the object. Hotter objects emit radiation at shorter wavelengths. For example, the Sun, with a surface temperature of about 5,500 degrees Celsius, emits most of its radiation in the visible spectrum. This is why the Sun appears so bright and we can see sunlight as visible light. Conversely, the human body, which has a temperature of approximately 37 degrees Celsius, emits most of its radiation in the infrared spectrum, making this radiation invisible to our eyes, but detectable with thermal cameras. This relationship indicates that the color of an object can give us insights into its temperature. When metals are heated to around 500 degrees Celsius, they begin to glow red. As temperature increases further, the metal starts to glow yellow-orange, which corresponds to shorter wavelengths than red light. A similar concept applies to stars. Blue or white stars are significantly hotter than red stars. By observing the color of a star, astronomers can estimate its surface temperature. In today's lesson, we delved into the emission of infrared radiation by objects and how it varies with temperature. We discovered that all objects emit radiation primarily in the form of infrared radiation due to their temperature. We noted that good absorbers are also good emitters. Black, dull objects absorbs and emit radiation well, while white or shiny objects do not. We learned that the intensity and wavelength distributions of emitted radiation increase with higher temperatures, leading hotter objects to emit more energy. The wavelength at which peak radiation occurs is inversely related to temperature. Hotter objects emit at shorter wavelengths. Using blackbody radiation curves, we visualize these concepts, understanding that hotter objects emit more energy at shorter wavelengths, which is crucial for applications like thermal imaging and astrophysics. This foundation provides a deeper understanding of thermal physics and energy transfer processes. Understanding how objects emit and absorb infrared radiation is crucial for applications ranging from thermal imaging to understanding stellar temperatures. Watch the rest of the GCSE physics course at Sophos Education.